So let's make a start. So for this lecture for S22334, so for those of you who were yesterday, let's recall or recap what we were doing. So we were talking about random variables which are now jointly defined. So the idea is you have an experiment with two functions defined on the sample space S, and these functions for every point in the sample space, they provide you a real number, okay, and the collection of real numbers that the random variables provide, i.e. the range of these random variables, are potentially countable or countably infinite, in which case that they are discrete, or that they produce values on products of intervals, i.e. that they are continuous. So where we left off yesterday was talking about the case where we had a bivariate vector, of your two-dimensional vector, of pairs of random variables x and y, and we were discussing how one constructs a probability distribution, or basically a probability mass function, on pairs of random variables. So this is the thing that we almost finished up with yesterday. So we had a pair of random variables x and y, and the joint probability mass function was denoted as highlighted. And we could compute the probability of any event by summing over all pairs of x and y such that they lie in that event A of the probability mass function. Okay, so that's where we were yesterday, and we had one example associated. That's what was example one is. So let's have a look at a couple more examples of probability mass functions for bivariate random variables. So this example, so you have two production lines for a given company, A and B, and they produce basically 5 or 3 machines respectively. And we assume that the number of machines that we produce is a random variable. So x and y, which are a pair of random variables, represent the two-dimensional pair of the number of machines produced by line A and line P. And we are given the joint probability mass function, that's on the next slide, and we're asked the following: what is the probability that more machines are produced by line A than line B? I think that chips doesn't make any sense in this. I think what the question means is machines, not chips. Okay, well, let's worry about the question in a moment. Let's look at the joint probability mass function of x and y on the next slide. So this is the joint probability mass function of x and y. So let's spend some time thinking about this. So on the this column here for y represents the possible machines made by line B. So line B could make 0 machine, 1 machine, 2 machine, 3 machines, and this row here, x, these values correspond to the possible values of x. So this is x is 0, x is 1, x is 2, x is 3, x is 4, x is 5. Okay. So what do the entries in this matrix correspond to? So this says this entry 0 and this entry 0. What this number 0 represents is the probability that the random variable x, i.e. the number of machines made on line A, is 0, and it's simultaneously that the number of machines made on line B is also 0. So that's impossible to happen. Respectively, if I go here to this red point here, the probability that x takes the value 2 and y takes the value 3 is defined to be 0.03. So this function is given to us. It's not, there's no way to derive it. Well, there is possibly, but with the information we have, we're just given this. Okay, so there's no question of where does it come from. It's an example. It's been constructed in some way unbeknownst to us. Okay, so each entry, as it says, each entry represents the probability that x takes the value xi, y takes the value yj for I and j in the set. I guess I is in the set 1, 2, 3, 4, 5, and this is the set 1, 2, 3. 1, 2, 3. Okay, so that's the probability mass function. Now, let us try to answer the question. So the question says, what's the probability that more machines are produced by A than line B on a given day? Okay, so this is it. So basically what we're asked for is the probability that the random variable x is strictly bigger than the random variable y. So what we do, so as you can see, so just as we said at the beginning of this lecture, the probability of any set A is the sum over all x and y values in the set A of the associated probability mass function. So this thing in red here at the bottom of your slide, this thing is are the entries of your the entries of the matrix are precisely your probabilities, and now we have to understand what the set A is. So as I said, we're interested in the probability that more machines are produced by line A and line B, or strictly that X, the random variable X, is strictly bigger than the random variable Y. Okay. Well, now this is relatively straightforward because you can see in bright yellow, okay, those yellow shaded things, the upper triangular part of this matrix, although it's not square, but this upper triangular part here, corresponds to all the cases where X is bigger than Y. So for example, if I take this entry here, X takes the value 1 and Y takes the value 0. So that is an element of the set A which represents X being bigger than Y. So I'm going to take that number. Now here X is 2 and Y is 0. So again, X is strictly bigger than Y. So I'm going to add that on. Here X is 3, Y is 0. I'm going to add that on. And so, for example, for all of these entries, I add them all together, and that gives me explicitly the probability that X is bigger than Y. Okay, so in this example, we just have a 4 by 6 matrix, so there's 24 entries here, so we can represent graphically what it is, the set of values we have to sum over. So just as it says here, this is exactly a manifestation of what I just said. Okay, so if you take the bottom line, the probability that X is bigger than Y is that X is equal to 1, Y is equal to 0, or X is equal to 2, Y is equal to 0, or so on and so forth. Okay, and if you like, all of those entries are representing mutually exclusive events, so the probability of this union is the sum of the probabilities. That's what we've got here. And so then basically, this is basically all the sum of all those entries which are shaded in dark yellow on the slide. So the answer happens to be 0.73. Okay, example 3. So you have a group of 9 executives. 4 are married, 3 have never been married, and 2 are divorced. Okay, and 3 executives are to be randomly selected for promotion. Again, for those of you who went to my tutorial, I don't think there's a good way to select people for promotion, but never mind, that's the way they're going ahead with it. Okay, so now in this example, capital X is going to represent the number of individuals that are selected and married, and Y are the number of individuals who are selected and have never been married. Among the 3, so as I say, selected means promotion in this context. And now what I'm asked to do, or we're asked to do, is to find the joint probability mass function of the random variables X and Y. Okay, and so this uses basically our combinatorial type construction. So the first thing is that we want to work out what are the total number of ways of selecting 3 executives from 9, and we know that, because we've seen that frequently many times. That's 9 choose 3. Okay, so if you did tutorial 2, this is kind of the denominator in those questions 3, well, definitely question 3, which was on those the poker hands. Okay, so that's the first thing. So the next thing is, let's think about the possible values that X and Y can take. Now we're going to take 3 executives out of this bunch of 9. Now we know that 2 of them are divorced, so at most we could take 2 individuals which were divorced, which means at least one of the 3 must be either married or never married. So X plus Y must be at least 1, right? We know that, because as I just explained, I'm only going to take out 3 individuals, so X plus Y is at most 3. Okay, so now X and Y could be 0, 1, 2, or 3. Okay, actually, no, that's not true. X plus Y must be at least 3. X plus Y must be at least 1. Okay, now, of course, X could be... so, yes, X could be 0, 1, 2, or 3. Okay, because there could be none of them which are selected and married. 1 could be married, 2 could be married, 3 could be married. And similarly, there could be 0, 1, 2, or 3 never married individuals, because 3 are never married. Okay, so those are both feasible scenarios, but we do have this constraint here. So that's the second thing. Now what we have to do is we want to work out the number of possible ways that we choose X individuals who are married, Y individuals that have never been married, and then the rest are divorced. So we know that we have 4 individuals that are married, and we're going to draw X. So there's 4 choose X possible ways to choose that. Okay, multiplied by, there are 3 never married, and there are Y possible ways to choose those individuals. 3 choose Y. Now the number of people that you can choose who are never, who were divorced, there are 2 divorced individuals, and then 3 minus X minus Y are the number of divorced individuals you can choose. So note that this takes into account the fact that you may never choose, you may choose 2, for example, divorced individuals, or 1 or 0. Okay, so the joint probability mass function of this random variable X and y, random variables X and Y, is basically the number of ways you can choose X, Y. You can basically choose the individuals, divided by the total number of individuals, and you have some constraints. So here the X must be and Y can lie in the set 0, 1, 2, and 3, but you must have this constraint. Okay, and if you sum over all possible values of X and Y, there aren't that many of them, you're going to get back 1. And that's, like, I suppose that's an exercise for reader. This probability mass function is explicitly 0 if, for example, X plus Y is exceeding 3, right? Because it's not defined otherwise. It doesn't fall into our case. Okay, and you can write down the probability mass function. So because X and Y only have 3 possible values, 4 possible values, and some of them are not allowed. So for example, if you take this entry here, I take X is 2 and Y is 2, well X plus Y is 4, so there's no chance we can take the value here. So this triangular part of this matrix are all zeros, because in this case the constraint X plus Y being at most 3 is violated. So again here I have X, Y is 3, X is 1, so 3 plus 1 is 4. Okay, and then basically in this case they can't, of course, both be 0, because there has to be at least one individual who's chosen who's married or never married, because there are only 2 divorced individuals. Okay, so this one is also 0. And these numbers, how do you obtain them? Well, you're just substituting, for example, X is equal to 1, Y is equal to 1 into this formula to get these numbers. Okay, so something that's important to note, you can compute row and column totals, and that's going to become important later on in today's lecture, I hope today's lecture. So this is the row, these are row totals. Okay, and actually what this row total represents, of course, that means I've summed 3 over 84, 6 over 84, 1 over 84, and that's 10 over 84. That represents actually the probability that X takes the value 0. Similarly, I can look at the column total, so here 1 over 84 plus 0 plus 0 plus 0, that's the probability Y is equal to 3. Okay, so these correspond to so-called marginal probabilities, and I'm going to define that later on. I'm just telling you as a matter of fact what's the interpretation of those row and column totals. The key point is if you sum those column totals, you're going to get back 1. If you sum those row totals, you get back 1. Okay, so this cannot be a valid probability mass function without those properties that the sum of the row totals are 1 and the sum of the column totals must be 1. Okay, you must have that for this to be a valid probability mass function. Okay, sorry about that. Okay, so that was the case of discrete random variables, and we'll see, well, you will see more examples in your tutorials as you get to them. Let's talk about the case where now X and Y are random variables which are continuous. So we let X and Y be 2-dimensional random variables. Again, that means that they're simply functions on the sample space. And basically they assume all values in some region of the Euclidean plane R2. Okay, so that basically means I can take an interval of R, I can take another interval of R, and then basically we're constrained in some square or circle or however you want to define that region. Okay, so the plane, again, like I said yesterday, this Euclidean plane R2, you can just think of your X and Y graph, and that's defining your support of your random variable. Okay, so now if basically f of x, y is called the joint probability density function of the random variables x and y, if it satisfies the following conditions. Okay, so these are kind of should be expected because we already know what they are. So remember, in the density case, it does not represent the probability that x is equal to x and y is equal to y, because that is 0. But first of all, just a remark, first of all, the point is that this function is non-negative for any pair of points x and y which lie in the region R, x, y. So this is the range of values of the random variable x and the range of values of y simultaneously. Okay, so it's a non-negative function. It must integrate to 1. Okay, that is, I take the function, I integrate over all possible values that x and y can take, and I get back 1 because it's a density function, probability density function. Okay, if you prefer, you can take it like this. Okay, they're equivalent because basically if the function f of x, y is 0 in some region outside, i.e. if r of x, y is a subset of the R2, then it will be 0. So these things are equivalent conditions. Okay, let's have a look at some questions, examples associated to joint probability density functions. Okay, so now we're given a two-dimensional continuous random variable, pair of random variables x and y, and the joint probability density function, PDF, is defined to be x squared plus xy over 3 if x is between 0 and 1 and y is equal to 0 to 2, and it's 0 otherwise. Okay, and we want to compute the probability that x plus y is at least 1. Okay, so how do we do this? Okay, well, it's not very important. So basically, first of all, before I say anything, so I just want to jump ahead just to tell you what is the region of support of the random variable. We can forget about the rest of this slide. I'm going to explain it in a moment. So here, this is the xy plane. X goes between 0 and 1, y goes between 0 and 2. So in this region, the probability density function is non-zero, but if I took a point here, the probability density function is 0. So that's what this thing means when we write this thing down. Okay. So what are we going to do in this example? We're going to do a couple of things. First of all, we want to check it's a joint PDF. Well, obviously this part's 0. I didn't have to check it. Now, if x is between 0 and 1 and y is between 0 and 2, so clearly this is positive whatever x I take. Because x and y is positive, x times y are non-negative, so this is non-negative. So this whole function is non-negative. So clearly this function is non-negative. That's good. The other thing we have to check, more importantly, is that the integral over the support, i.e. this third bullet point, is it precisely 1? Because if it isn't, it's not a probability density function. Okay, so hopefully you have done double integration before. If you haven't, we're going to learn it along the way. It's pretty much doing integration once and then integration again. So basically, I want to compute the integral between minus infinity and infinity for x. This means integrate x first. Then that integral is again integrated with respect to y between minus infinity and infinity. Okay, now the key point is, as I stated just a moment ago, the probability density function is precisely 0 outside this rectangle. So outside this rectangle we're 0. So we only need to integrate over this rectangle. So x goes between 0 and 1, and y goes between 0 and 2. Okay, so this is this thing, and this is this f of x, y that was written on the previous slide. So what I'm going to do now is I'm going to integrate, first of all, the thing to do here is I just ignore y, and I'm just going to integrate this thing. So what this thing is, if I forget about this part, this dy part, is basically the integral between 0 and 1 of x squared plus xy over 3 dx, where y is a constant. Okay, so it could be, doesn't matter what it is, I'm just going to fix it, and I'm going to do my integration as if y is fixed. Okay, so what that is, so if I integrate x squared, that's x to the 3 over 3. If I integrate x times y over 3 with respect to x, I get x squared over 6 times y. Y is a constant, so if I partially differentiate this function with respect to x, I'm going to get 2 times x times y over 6, which is precisely xy over 3. Okay, so similarly, if I differentiate this partially with respect to x, I'm going to get 3x squared over 3, which is x squared. Okay, so that's where I get, so basically this part here is just, this is just an ordinary integral, if you like, with respect to x, and you can ignore y being, it could be anything, but it's constant for the purposes of integration with respect to x. So now what I do is I evaluate this integrand, this indefinite integral between 0 and 1. So when x is 0, I don't have to worry because this whole thing is naught. So I just set x is equal to 1. So I'm going to get 1 over 3. That's what I get here. And now I'm going to get 1 times y over 6, which is y over 6. Okay. Now my job is not complete because now I need to integrate the resulting quantity, which is explicitly a function of y with respect to y. So I have 1 over 3 plus y over 6, and I integrate now this with respect to y. Okay. And now this is a relatively straightforward task because we're used to doing these things, those single integrals. So now, if I integrate y 1 over 3 with respect to y, I get y over 3. If I integrate y over 6 with respect to y, I get y squared over 12. And the integral is now between 0 and 2. Okay? And so now, again, if I evaluate that function at y equal to 0, I'm going to get 0, so I don't care about that case. I only care about the case when y is equal to 2. So this integral is now 2 over 3 plus 4 over 12, and that's equal to 1. Okay? So what have we deduced from this calculation? We've deduced that the function fxy is non-negative and that it integrates to 1. As a result, it is a probability density function. Very good. Okay, so now we go back to the question at hand. So the question is asking us, I want to compute the probability that x plus y is bigger than 1. Okay. That's the same as computing the complement, 1 minus the probability of the complement. So the complement of the... You don't have to do it this way, to be honest, but I'm just going to do it the way that it's in the solution. You can do it another way. You can compute the probability of A explicitly, but apparently we're going to do it a different way. So the complement of A is that x plus y must be less than 1. Okay? And since the probability of the set A is 1 minus the probability of the complement. So let's think about how to compute the probability of the complement. So what I have to do, so just as you did in the case where x and y are discrete, instead of summing over the region A, I want to integrate over this region A of this thing here. And okay, and it's slightly bad notation actually. But anyway, so this is the set x plus y such that x plus y is less than 1. That's what that lower integrand really means, although that's not really what it's written. Okay. So now, what's the region of integration that I have? Okay, so remember that, as I said a moment ago, the range of values of y is 0 to 2. The range of values of x is 0 to 1. But now this set has a constraint that x plus y must be strictly less than 1. Okay, so this line here is the line y is equal to 1 minus x. Okay, that's the line. And so the region I want to integrate this bivariate function on is this thing in red. So how do I integrate over this region? Okay, so here we're going to go with respect to y first. So if you want to integrate this function with respect to y first, one way to do it is the following. You draw a line parallel to the y-axis with an arrow pointing upwards. Okay, and then you see where it enters the region and where it leaves the region. So in our case, y enters the region when it's equal to 0, and it leaves the region when it's equal to 1 minus x. So what that means is the region of integration with respect to y is 0 to 1 minus x. Now, to obtain the region of integration with respect to x, I have to kind of move my arrow from the left to the right. So we start when x is 0, and I end when y is equal to 1. Okay? And so that gives you the integral range for x. X is 0, 1, y is 1, 0 to 1 minus x. Okay? And now all I'm left with the task of doing is computing this integral first with respect to y and with respect to x. Note that you could do this integral with respect to x and then with respect to y if you like. If you want to do x then y, what you do is you draw a line parallel to the x-axis. So it's pointing from left to right as you look at it. So x could go between 0, and this line is 1 minus y, and then y goes between 0 and 1. Okay, here we go y then x, you can do x then y. And generally for any function that we look at in this course, integrating one way or the other doesn't matter, you get the same integral. In fact, it's true for almost anything in mathematics which you encounter in even at the graduate level, really, integration doesn't matter which way you do it, almost always. Okay. So we're doing y then x. You could do x then y. Also, you could just deal with the set x plus y greater than or equal to 1. It's no more complicated, to be honest. You're just looking at this region here. Well, you have to do a bit more thinking in that case, but still, you could still do it that way. It turns out it's actually easier to do it this way, but I don't think it's that much harder to do the other one. Okay, so now I just compute this double integral, and I do 1 minus it, and we have the solution. Okay. Oh, okay, he's explaining it there. Okay, well, I've explained it to you. So then, how to compute the integral? So first of all, we integrate with respect to y. So this one, if I integrate with respect to y, x squared times y. This one, if I integrate with respect to y, that's going to be x times y squared over 2 times 3. So it's x times y squared over 6. Okay, so now I want to compute the integrand, or this function, and it goes between y0 and 1 minus x. So if y is equal to 0, I knock out the whole function, so I don't care about that. And when y is equal to 1 minus x, I'll get x squared times 1 minus x plus x times 1 minus x all squared over 6. Okay, and now I just have to compute the integral with respect to x in the limit 0 to 1. Okay, so these are not so difficult. Okay, so then you can do x squared times 1, so that's x to the 3 over 3. X squared times minus x is x minus x to the 3 is x to the 4 over 4. Okay, and so the other one, okay, you can do it. You can multiply out these brackets, so I get 1 minus 1 plus x squared minus x minus 2x. Okay, and I multiply by x, so I get x squared over 2, this is x over 6, times the, minus 2x squared, you get x times 1, x over 6 times 1 minus 2x times x over 6 plus x squared times x over 6. So if you integrate those three terms, you're going to get x squared over 2, you can leave the 1 over 6 x squared. So if you differentiate this, x squared over 2, you're going to get the x, that's from the x times this. 2x cubed over 3, that's x. If I differentiate, I'm going to get the 2x squared, that's from this minus 2x here. X to the 4 over 4 gives you x to the 3, that's from this one times x squared. Okay, and then I integrate this whole, then evaluate the whole thing between 0 to 1. So again, when x is 0, I don't care, the whole thing is 0. And when x is 1, I'm going to get a third minus a quarter plus 1 over 6 times a half minus 2 over 3 plus 1 over 4. So the answer is 1 minus 7 over 72 is 65 over 72. Okay. I think that hopefully that was relatively clear. I mean, basically, x is 0 knocks the whole thing out. If you're lazy, you can do this by integration by parts, although there's no reason to do it that way. Okay. Let's look at example 2. So example 2 is actually much easier. So in this case, you have a joint PDF. There's a typo, by the way. There is a typo here. This should be a y. So this is the joint PDF f of x y is equal to 12 over 13 x times x plus y. X is in the region 0 to 1. Y is in the region 1 to 2. And the function is defined to be 0 otherwise. Now we introduce the set A is the set of x and y's such that x is between 0 and a half and y is between 1 and 2. And we want to find the probability that the pair of random variables x and y are in the region A. Okay. Okay. So let's have a look. So there's the calculations, but the simple thing is first of all to compute the region. So remember that x goes between 0 and 1 and y goes between 0 and 2. So the whole PDF has support on this square. Okay. Now what we're asked to do is we're going to ask to compute the probability that x lies between 0 and a half and y lies between 1 upon 2. So this is this half of this square here. So this is our shaded region. Okay, so now if we integrate with respect to x first, x goes between 0 and a half, right? That's this thing here. And y goes between 1 and 2. So we get 0 and a half, 1 and 2. Okay, this is considerably easier than the previous example because we don't have to compute the line y equal 1 minus x. Okay, and then we're just in the game of playing double integration and double integration with polynomial functions. So now I want to integrate this function. So I can take 12 over 13 outside. That's just a constant with respect to x and y. So now what do I want to do? I want to integrate the function x squared plus xy first with respect to x. So the integral of x squared is x to the 3 over 3, and the integral of xy is x squared y over 2. Y is a constant. I'm evaluating this function between x is 0 and a half. Okay, so as in our previous example, if x is equal to 0, that knocks out the entire function, so I don't care. And if x is equal to a half, I'll get 1 over 2 to the power 3 over 3 to the times 1 over 3, sorry, which is 1 over 24. And I get basically a quarter times a half is an eighth, so I get y over 8. And y is going between 1 and 2, so I have to do my second integration. So this one's straightforward. So this one, I take the factor, 1 over 24 outside, or 1 over 8 outside, sorry. What is it doing here? He's taking 1 over 24 out, okay. So we take 1 over 24 out, apparently that's going to give you, yes, 1 over 26. So the integral of 1 is y, and the integral of this thing, when you take 1 over 24 out, is y squared times 3 over 2. Okay, and I go between 1 and 2. Okay, and if you evaluate this now, when y is 1, you have something slightly different, but you evaluate first this thing at 2, and you subtract the case of this thing when y is 1, you multiply the answer by 1 over 26, and apparently that's equal to 11 over 52. Okay, and that's the probability of that region A. Okay, hopefully that was clear. Now we're moving on to the case where I've got a joint probability distribution on pair of random variables x and y. Okay, that's a joint PDF or a joint PMF. But of course, what I might be interested in is just x or y by themselves. And this is the notion of a marginal probability distribution. If you like, what we're discussing here is essentially the random variable generalization of the law of total probability. There's nothing more than that, actually. Okay, so let's start with the case that x and y are discrete or continuous. They're a pair of random variables, and they have a joint probability mass or density function, which we denote by this f subscript x and y to denote that this is a joint distribution on x and y, and little x and y being the arguments of the function. Okay, so the marginal probability distribution of x or y by themselves is defined as follows. So if I consider the discrete case, what I do, the marginal probability mass function of x is the following. I sum over all possible values of y of the joint probability mass function. And if I want the marginal probability mass function of y, I sum the joint probability mass function of x and y over all possible values of x. Okay, that's a definition. In the continuous case, all you do is you replace your summation with your integration. So the marginal density function of the random variable x is simply the joint PDF of x and y integrated over all possible y's. Okay. Similarly, the marginal probability density function of y is the integral over all possible values of x of the joint probability density function of x and y. Okay. And this, if you want to think about it more deeply, is nothing more than the law of total probability. In fact, you can derive it from that. It's not important to derive it, but you can. All right, so let's have a look at example 1. So we start with the case of discrete. So So we look at example 1, refer to the example 2 of section 3.2.1 on page 3 to 14. Okay. And we want to find the marginal probability mass functions of x and y respectively. So let's have a look at that example, page 314. Okay, I'm going the wrong way. Okay, here we are. Yes, this is the one. Okay, so what I want to do is I want to find the marginal probability distribution of x and y respectively. Okay, so I can do that immediately from this table. Okay. So first of all, I ask the question, what is the probability that y is equal to 0? Okay. Well, the probability y is equal to 0 is by definition the sum. So I fix y as 0 and I sum over all possible values of x. That's basically the definition that we had precisely for the marginal probability mass function. So the probability that y is equal to 0 is equal to 0.01 plus 0.02 plus 0.05 plus 0.06 plus 0.08 is 0.22. But that's not the joint, that's obviously not just the marginal probability mass function, because I've only got the marginal probability that y is equal to 0. Now, the probability that y is equal to 1 is 0.01 plus 0.03 plus 0.04 plus 0.05 plus 0.05 plus 0.07 is 0.25. Similarly, the probability that y is equal to 2, so I sum across the columns to get 0.29, and the probability that y is 3, again, summing over the columns, is 0.24. So this collection of numbers, that's the probability that y is equal to 0, the probability y is 1, probability y is 2, probability y is equal to 3. Okay. Now, if I want to find the probability mass function of x, I do a different thing. So now here I fix x is 0, and I want to find the probability x is equal to 0. So I do 0 plus 0.01 plus 0.02 plus 0.02 is 0.05. The probability that x is 3 is 0.05 plus 0.05 plus 0.06 plus 0.04 is 0.2. And similarly, you just sum over these rows, okay? And so the marginal probability mass, the probability mass function of x marginally is this collection of column totals. And so note that the row totals sum to 1 and the column totals sum to 1. This is the probability mass function of y, this is the probability mass function of x, and this is the joint probability mass function of x and y. Okay, hopefully that was the solution to this example, otherwise I've been telling you nonsense. Let's have a look, yeah. So this is exactly what I've just been telling you. It's just a description of those numbers. Okay. And so we note that, of course, that every entry of this table, this is basically a summary of those row totals, I think, or the column totals, sorry. So this is the summary of those column totals I was just discussing. Every entry is non-negative, okay, and they sum to 1, okay. That's what this thing says right at the bottom. Okay, and this is just the case of y, okay, and that's the case. These are the column totals or row totals, okay. So that's what I just discussed a moment ago. Okay, so that's basically so as I said, I'm anticipating what's in this notes. So the red entries in this table, which is just a kind of summary of the table, so the red entries are the joint probability mass function. So again, this represents the value that x is 3 and y is 2. These purple values, which are the bottom values, this is the marginal probability mass function of x, and the light blue are these totals on the end, are the marginal probability mass function of y. Okay, so graphically that represents all the quantities you've gotten. And again, if you want the 0.25, I sum across these columns. Okay, example 2. So now we refer apparently to example 2 of section 3.2.2 on page 328. Okay, that's just something we just saw a moment ago. So that basically is the joint PDF that you see summarized in front of you. And I want to find the marginal PDF of x and y. Okay, this is not too difficult, this one. Okay, so we start with x. So first of all, what do we know? We know if x lies outside the interval 0, 1, then the joint PDF of x and y is 0. So we must constrain, first of all, x and y to be in 0, 1. Otherwise, the marginal is precisely 0 from the beginning. Okay? So now, the marginal PDF of x is by definition the integral over all possible values of y at the joint PDF of x and y with respect to y. So if I want x, I integrate y. If I want y, I integrate x. Now, of course, this joint PDF is only defined with y, is only non-zero, if y is in the interval 1, 2. So this integral is precisely the same as if I just integrate between 1 and 2 of the joint PDF, and now I'm integrating with respect to y. Okay, so now life is going to be relatively straightforward because I'm just integrating the function with respect to y, taking x constant. So this thing is equal to, so first of all, 12 over 13 comes out. I have x squared, so x squared integrated with respect to y is x squared times y. And then I have x times y integrated with respect to y is x times y squared over 2. And I go, and then I evaluate this function with respect to y is 1 and 2. So I take evaluated to 2, and I subtract the answer when y is 1. And if I do that, I get this function 6 over 13 x times 2x plus 3. So, of course, please note that the resulting function is explicitly a function of x only and not a function of y. If you want to compute the marginal PDF of x, it can only be a function of x. It cannot be a function of y. If you get y in your calculation at the end, you have made a mistake. Okay? And so the marginal, as I said, if x is outside the regions 0, 1, you get 0. Okay, very exciting. Now, to find the marginal PDF of y, what do I do? So now remember, if y lies outside the region 1, 2, then I have the joint PDF of x and y is equal to 0. So I don't need to worry about that case because I get that the marginal is 0 outside that interval. So as I did very similarly in the case where I was trying to find the marginal for x, the marginal for y is the joint PDF of x and y, and I integrate over x all of the possible values that x can take. And all the possible values of x can take is between 0 and 1. And now I have my joint PDF, and now I integrate critically with respect to x. Okay, so basically now I can take my factor 12 over 13 outside of my integral. The integral of x squared is x to the 3 over 3. The integral of x times y with respect to x is x squared times y over 2. Now this thing, when x is equal to 0, is basically 0, and when x is equal to 1, I'm going to get 1 over 3 plus 1 over 2 times 1 times y. So basically the thing at the end is 2 over 13 times 2 plus 3 times y, when from y is in this set, and it's 0 otherwise. So again, remember that the function I've computed is explicitly only a function of y and not x. If I get x in my final calculation, then I have a mistake. Okay. Right, let's have a look at conditional PDFs and conditional PMFs. So remember that if you cast your mind back a couple of weeks, we were computing the probability of A given B and B given A, and that was the probability of A given B is the probability of A and B over the probability of B. Okay, that's something we learned a while back. You can obtain exactly an equivalent definition for random variables. So let x and y be discrete or continuous two-dimensional random variables with a joint probability mass or density function written like that. And let f sub x and f sub y be the marginals, exactly those quantities we were investigating in our previous two examples. Okay, very exciting. What's our definition? Then the conditional density, I'm going to say the phrase density or mass function. It's not the distribution, because you can confuse that with probability distribution functions, of y given x is defined to be, so the conditional PDF of y given x is the joint PDF of x and y over the marginal probability mass, marginal density function of x. This is if x and y are discrete or continuous, only in the case that the function f of x is strictly positive. Okay. So that's a conditional PDF of y given x, and precisely you can get the conditional density function or mass function of x given y precisely using what you might expect is the analog. So the joint density function of x and y is on the right, and of course instead of dividing by fx of x, we divide by fy of y, because we condition on y. And again, this is only defined whenever the density function in the denominator is precisely positive. Okay, so let's make a couple of remarks, and I think we're going to have our break. Yes, let's have to make our remarks, and then we have our break. So, oh, sorry, what the heck have we done now? Sorry. Just come all the way to the end. My dreams. Okay, where do you go there? We've got a lot of examples coming up, which will make you so very excited. Okay, here we are. Okay. The conditional probability mass functions, or PDFs, satisfy all the requirements for a one-dimensional probability density function or a probability mass function. That is to say that if I consider the conditional density function for, when I say density, I mean PDF or PMF. It's an exchangeable phrase for me. So that means that for any fixed y, the conditional density for x is strictly a non-negative function because it's a probability density function in x for y fixed. And again, the density function for y given x for every fixed x in the domain is a non-negative function. Okay, it must be because we are computing the compute probabilities from it. Also, we just note that for continuous or discrete random variables exchangeably, if I integrate or sum the conditional density function for x given y over all x's, I get back 1. Okay. Similarly, if I take the conditional PMF or PDF of y given x, I get back 1. They are probability density functions here in y and here in x. Okay. So make it clear that basically they are density functions. It's just you're considering y as a constant. Okay, basically you can also rearrange this formula. If I know the conditional and the marginal, I can get the joint. Okay, so remember that what we had were events is the probability of A and B is the probability of A given B times the probability of B. This is the analog for random variables. So the joint PDF of fx and y, if fx of x is positive, is equal to the product of the conditional times the marginal. Or if you prefer, you can go the other way around. If fy of y is positive, the joint of x and y is the conditional of x given y times the marginal on y. It's exactly the analog for events. Okay? And indeed, there exists a construction to prove these results explicitly from the ones I mentioned about events. It's just at a technical level much higher than even the stat majors will see. Okay, very good. So we've got to an example, so we're going to have a break for 5 minutes. We'll resume at 14:51. Okay, so let's resume. So we've got a look at these examples here, 5 examples. I think once we get to the end of these examples, if we do, then we will stop. But if we don't, then we will not stop. We'll stop it when we're supposed to stop. Okay, so the first example, you have an experiment, you flip a fair coin 3 times, and so the fair coin, so that's obvious. So now we define x as being the number of heads that you get, or the number of heads that you've got up to the last flip. Okay, so that's kind of badly phrased, but, and y, so that's basically it's whether or not you get a head on the last flip. The y is the total number of heads that you get in your 3 flips. Okay. And I want to find the distribution of y, the number of total heads that I get in my 3 flips, conditional on knowing that my last flip was a head. Okay. This one is a bit more intuitive. So let's have a look. So let's look at a joint probability mass function of x and y. Okay. So basically we have, of course, all our possible outcomes, HHH, THH, HTH, HHT, TTH, blah, blah, blah. Okay. Now, in this situation, x, which is the last, basically the last outcome of the last flip, h is 1, and y is the number of heads, which is 3. Similarly here, tail HH, so your last flip, you got 1 head on the last flip, and you had 2 heads in total. So for example, here this is 0, 0, because I got no heads on my last flip, and I never got a head during my 3 flips. And the probability of each of these outcomes is 1 upon 8, because there are 3 independent events, 1 over 2 times 1 over 2 times 1 over 2. Okay, so for example, here I got a head on my last flip, and my total number of heads was 1. Okay, so I can write down my joint probability mass function of x and y from the beginning. Okay, x can only be 0 or 1. Okay, and y could be anything from 0, 1, 2, or 3. Okay, so for example, the probability that I get 0 total number of heads, and 0 is the last, and no head on my last flip is 1 upon h, because that's TTT. For example, if I take 1 and 0, right, so 1 and 0 happens here, that's an eighth, and 0, 1, so I get 0, 1, 0, 1. Okay, so that's 1 over 4. 1, 0, well, that can't happen. I can't get a head on my last flip and then get no heads in total. Here, this is 3 heads and 1 on the last. So that's basically this one, HHH. And so, for example, 2, 1, right? I've got this one and I've got this one. So it's an eighth plus an eighth, where do I get a quarter? Okay, so all these red values have been deduced precisely from this table here. Now we know how to compute now the marginal probability mass functions of x and y respectively. Because to get the marginal probability that x is equal to 0, I just do an eighth plus a quarter plus an eighth plus 0 is a half. And the probability x is 1 is a 0 plus a half plus a quarter plus an eighth is a half. Respectively, I can get the probability y is equal to 0, because that's an eighth. The probability that y is equal to 1, that's a quarter plus an eighth. The probability that y is equal to 2 is an eighth plus a quarter is a 3/8. The probability that y is 3 is an eighth. Okay, so now what do I have? I've got my joint probability mass function, the reds. I have my marginal probability mass function of y. That's here. And the marginal probability function of the x is here. Okay, so now I can easily compute my conditional probability distribution or probability mass function of y given x is equal to 1. Okay, so the distribution of y given x is equal to 1 is the joint probability that x is equal to 1, y is equal to 0 over the marginal probability that x is equal to 1. Okay, so now f of x, y, 1, 0. Well, let's have a look at that. 1, 0, well that has 0, so I don't care about this one. It's going to give me 0 whatever happens. Okay, all my denominators, by the way, remember that fx of x is equal to half. So my denominator is always positive, so I don't need to worry about dividing by 0. Now the probability that y takes the value 1 given x is equal to the value 1, well that's the joint probability of getting both 1s over the probability that x is 1. The probability x is 1 is a half, that's always the case in here. The probability of 1, 1, well I can look at that. 1, 1 is an eighth. So I get an eighth over a half, that gives me 1 over 4. So similarly here, the probability that y takes the value 2 given that x is 1 is the probability that x is 1 and y is 2 over the probability x is equal to 1. F of x, y, 1, 2, well that's basically equal to 1, 2, that's a quarter. So I get a quarter over a half is a half. Okay, and similarly 3 given 1 is 1, 3 over 1. 1, 3 is here as an eighth. I get eighth over a half is a quarter. So the conditional probability mass function for y given x is equal to 1, basically the chance it's 0 is 0, the chance it's 1 is a quarter, the chance it's a half, 2 is a half, the chance it's 3 is a quarter. And note that if I sum now over all the possible values of y, I must get 1, and all these entries in the table must be strictly non-negative. It must be non-negative. Okay, so now we refer to example 1 of section 3.2.1 on chapter 312. Okay, so that is basically example 1 which we saw yesterday at the end of the lecture, which is the joint probability mass function for a pair of discrete random variables x and y is 1 over 36 times x, y, where x can be 1, 2, or 3, and y can be 1, 2, 3. Okay, and what we want to do in this example is compute the marginal probability mass function of x and the conditional probability mass function of y given x. Okay, so the first one should be relatively straightforward, right? We took this function, we sum this function for y is equal 1 to 3. And that's exactly what we do. So the marginal probability mass function of x is equal to, for x in the set 1, 2, 3, so I have the sum y is equal 1 to 3, 1 over 36 x times y. So x over 36 is a constant in this summation, so I take it outside. And now y sums from 1 to 3. That's 1 plus 2 plus 3, okay, which is 6. 6 times x over 36 is x over 6. And remember that x must be constrained to the set 1, 2, and 3. Otherwise, this marginal probability mass function is precisely equal to 0. Okay. Now to find the conditional probability mass function of y given x, I've got the marginal f of x. That's non-zero for x is in the set 1, 2, 3. So now what do I have? I have the conditional density mass function of y given x, it's the joint probability mass function over the marginal when x is constrained to be in the set 1, 2, 3. If x is a number, another number, the conditional probability mass function of y given x is not defined because the marginal probability mass function of x is 0. Okay, so this thing here is xy over 36. This is x over 36. The x cancels. 1 over 36 times 1 over 6 is 1 over 6, so it gives you y over 6. And y is in the set 1, 2, 3. Okay. Actually, in this case, you can actually prove that the random variables x and y are independent, but since we have not defined that yet, there's no point talking about it. Okay, example 3. So now example 3 is an example where x and y have this joint PDF. We should have seen that before, I hope. X lies in the set 0, 1, y lies in the set 0, 2. It's a little bit different, I think, than what we've seen before. And otherwise, the function is 0. And now what we're asked to do is to do two things. First of all, to find the marginals and then find the conditionals. And we'll focus on A and we'll return to B in a moment. Okay, so to find the marginal PDF of X, first of all, we know X must be between 0 to 1, otherwise the joint PDF is 0. Okay, so we constrain X to be in the set 0 to 1. Then the marginal PDF of X is simply the joint PDF of X and Y integrated over all possible values of Y. In this case, Y goes between 0 and 2 for this function to be non-zero. So we have x squared plus xy over 3. I integrate over y, and y goes between 0 and 2. Okay, so if I integrate this one with respect to y, I'll get x squared times y. If I integrate this thing with respect to y, I'll get x over 3 times y squared over 2, which is x times y squared over 6. Y goes between 0 and 2. And so, then when I evaluate it, y is 0 is 0. When y is equal to 2, I'll get x squared times 2. And I get y is equal to 2x over 6 times 4. But then I get that 2 times 3. 2 over 3, sorry. So, of course, if x is outside the range, I get 0. Okay, so that's my marginal for x. My marginal for y, okay, so that's my marginal for x. If you want to formalize it, that's how it looks. Okay, that's basically our calculation. Now the marginal for y, again, so if y does not lie in the region interval 0 to 2, the marginal PDF is 0, so I only focus on this case. And so by definition, the marginal PDF of y is the integral over all possible values of x of the joint PDF of x and y. Okay, so again, x goes between 0 and 1, and this is my joint PDF I had before. And now my task is to integrate this function explicitly with respect to x. So the integral of x squared is x to the 3 over 3. The integral of x times y over 3 is x squared over 2 times y over 3 is x squared y over 6. Looks pretty much like the question we had before. And now we go between 0 and 1. So if x is 0, of course, this function is 0, and if x is 1, I get 1 over 3 plus 1 over 6 times y. Okay, and that's my marginal PDF for y. So this is the formalization of the function. Okay, that's the marginal PDF. If you want, you can integrate that function between 0 and 2, and I hope to God that you get back 1. Very good. Okay, now what I want to do, I want to confine, let's remember ourselves, that the conditional PDF of y given x, the conditional PDF of x given y. Okay, so the conditional PDF of x given y. So remember, if x does not lie in the interval 0 to 1, the marginal is 0. So basically, I have to constrain my x to be in that region. So the conditional PDF of y given x then is the joint PDF of x and y over the marginal of x. Okay, the joint PDF of x and y apparently is like that. The marginal which we computed in part A, it looks like this, and y must lie in the set 0 to 2. Okay, and if you like, you can simplify this ratio by removing the common factors. Okay, so that's the conditional PDF of y given x. It's simple algebra. It's just computing a ratio of things we have calculated already, and you just have to be careful. You need that y is in 0 to 2, and you must have that x is in 0, 1. Of course, this is a function. This is a density function which is random in y, but x is fixed. Okay, so for example, if x is equal to 0, then the conditional PDF of y given x is basically, I just substitute y is equal to, x is equal to 0 in this function. Okay, and it's like that. If x is 0.5, again, all I do is I substitute x is 0.5 in this function. Okay, and that's what the function looks like. All right, now to find the conditional PDF of x given y, we're again playing essentially the same game. Y must be in the region 0 to 2, otherwise the marginal is 0. So again, it's the same thing. The conditional of x given y is the joint x and y over the marginal y. Okay, the joint x and y, that's given to us in the question. The marginal y, that's something that we computed at the start in part A. And we substitute, this is our expression, joint x and y. This is our marginal for x, marginal for y, excuse me. X is constrained in this interval, y is fixed in this interval. And this is, after doing some simple simplification, basically multiplying through by some factors, 1 over 6 in fact, on both numerator and denominator, gives us precisely our conditional density for x in y. It's a density function in x for any fixed y in this interval. So for instance, if I let y equal 0, then my conditional PDF of x, well, if x is between 0 and 1 is 3x squared and otherwise 0. If y is 0.5, the conditional PDF is basically for x in this interval 0 to 1, it looks like that. Basically, I'm just substituting x is equal to, y is equal to 0.5 in this function. Okay, oh, that was surprisingly easy. Okay, example 4. So example 4 goes back to our example on fast food restaurants, which have a drive-up and walk-up window. Again, it's virtually the same thing in my mind, except you have to have the road for the former. So now, on a randomly selected day, x is the proportion of time that the drive-in facility is in use, and y is the proportion in time that the walk-in window is in use. Okay, so x and y are random variables which are defined in the set 0, 1, and we are given that the joint PDF is this. Okay, so this is the joint PDF for these pair of random variables, x and y. Okay, very exciting. We're asked the following questions. We're asked to find the probability that neither facility is busy for more than a quarter of the time, i.e. the probability that x and y lie in the intervals 0 and 1 upon 4, respectively. Okay, and we'll worry about B in a minute, otherwise we're going to forget what it is by the time we get there. Oh, it's C and D. My God, we're going to be here all day. Okay, part A. So now we want to compute the probability that x lies in the interval 0, 1 upon 4, and y lies in the interval 1 upon 4. This is straightforward, because now all I have to do is I just take my joint PDF, which was the thing that you saw at the beginning of the example. I integrate x between 0 and 1 upon 4, and then I integrate y between 0 and 1 upon 4. And as I have said, you could do y first, then x. It will not matter here. Okay, very good. So now we split the, okay, so then we take the factor 6 over 5 outside the integral. That's what you've done there. Excuse me, and now the integral of a pair of a pair of additive functions is the sum of the integrals. Okay, so I take this one, I integrate x, dx, dy. These are my ranges, and I take y squared between dx, dy. Okay, and so now I just do these two double integrals. So the integral with respect to x, that's x squared over 2, goes between 0 and 1 upon 4, and I still have to do an integration with respect to y, except I'm in a good position because it's not going to depend on y. The integral of y squared with respect to x is just going to be y squared times x. X goes between 0 and 1 upon 4. Okay, so this one is going to give me a constant. I can take it outside. This one I'm going to have do some more integration. Okay, so what I'm left over with is 6 over 5, that was my constant. The resulting value of the thing that I had before is 1 over 4 squared. Okay, so like I say, it's a constant. This one is y squared over 4. Okay, if you're wondering, I'm just going to value anyway. X is 0, and I get 1 upon 4 times y squared. Okay, so now doing the resulting integrals, so this one on the left, this part here, it's very straightforward. It's just going to be y over this, y multiplied by this constant, which is 1 over 32. Y goes between 0 and 1 upon 4. This one is going to be y to the 3 over 3 times 4 is y to the 3 over 12, between 0 and 1 upon 4. Okay, so this function when y is equal to a quarter, and y is 0 doesn't matter, y is a quarter, y is 0 doesn't matter. So if you do 6 over 5 times these things here, you're going to get the answer, which is 0.0109, apparently. Okay, so that's part A. Okay, that seems to be right, reasonably okay. Now, this is asking us the question, find the PDF of x. Okay. And then, hence, find the probability that x is in the region 1 over 4, 3 over 4. Okay. So these are all words, but the thing in red is the thing you want to calculate. So if you like algebra more than you like words, that's all you have to do. If you like, you can read this and interpret this was what you want. Okay, so first of all, find the marginal of x, and then find the probability x lies in this interval. Okay, part B. So now we know that x and y lie in the interval 0 to 1. Okay, so first of all, to find the marginal PDF of x, x is constrained to the interval 0 to 1. Okay, now what do I do? To find the marginal PDF of x, I compute the joint PDF of x and y, and I integrate with respect to y over all possible values of y. In this case, remember that y goes between 0 and 1. So this is my joint PDF. I'm integrating with respect to y. I'm going between 0 and 1. So the integral with respect to y is straightforward. 6 over 5 comes outside. The integral of x with respect to y is x times y. The integral of y squared with respect to y is y to the 3 over 3. And now I integrate this function between 0 and 1. And I'm going to get a function in x in this case. When y is 0, I don't care. So I just have to substitute y in here. So I get 6 over 5 times x plus 2 over 5, which is 6 over 5 times 1 over 3. Okay, and so the marginal PDF of x is 6 over 5 times x plus 2 over 5 if x is in the interval 0 to 1 and it is 0 otherwise. Okay, now what do I want to do? I want to compute the probability that x lies in the interval between 1 quarter and 3 quarters. Okay, and that amounts to another integral. I'm just computing the integral between 1 over 4 and 3 over 4 of the marginal PDF of x. Okay. And so that's straightforward. The integral of 6 over 5 times x is 6 over 5 times x squared over 2, which is 3 over 5 times x squared, plus 2 over 5 times x between a quarter and a third. So I evaluate this function as 3 quarters, and I subtract the value of this function of x is equal to 1 over 4. And if you do that, apparently the answer is 1/2. Okay, so that's part B. Okay, let's have a look at part C. Okay, let's see, what is the question? So part C. So given that the drive-in facility, I prefer in, I don't know what drive-up really means. It sounds like something strange slang to me. Drive-in facility is busy 80% of the time. What is the probability that the walk-in facility is busy at most half of the time? Okay, so what does this mean? I want to compute the probability that y, which is my walk-in facility, is at most a quarter, given that x is equal to 4 over 5. Okay, so what is the scenario here? What I want to do is I want to compute the conditional PDF of y given x, and then I want to compute the integral between 0 and 1/2 of y given x for the conditional evaluated when x is equal to 4 over 5. Okay, so that's what I want to do. Of course, saying what I want to do and actually doing it is a different situation. So here he's going to say, well, I'm just going to fix x is 4 over 5. I only need to answer the question when x is 4 over 5, so why not just do it when x is 4 over 5? You can do that. I prefer to have done it generally, but doesn't matter. So then the joint PDF of x and y when x is constrained to be equal to 4 over 5 is the joint PDF when you evaluate the function, the joint density function at x is 4 over 5 and y is y, and y has to be between 0 and 1, divided by the marginal PDF of x evaluated when x is equal to 4 over 5. Okay, now this marginal PDF, I have computed it, or we have computed it. This is exactly this function. So I evaluate this function when x is 4 over 5. Okay, that's my denominator here. My numerator is the joint PDF, and I evaluate x is equal to 4.5 and remind ourselves that y is constrained to the interval 0 to 1. Doesn't matter if doesn't matter if it's less than or equal to or strict inequalities. It's the same things. Remember, the probability of a point is 0. Okay, so the evaluation of this function of the joint PDF when x is equal to 4 over 5 is apparently like that if y is in the set 0 to 1. Okay, so that's the conditional PDF of y given x is equal to 4 over 5. And now I just want to integrate this over the interval 0 to 1 upon 2 in order to obtain my solution. So the probability that y is less than or equal to a half given x is equal to 4.5 is the integral between 0 and 1 upon 2. The minus infinity, it doesn't matter because remember that x, if y is between minus infinity and 1, that the conditional density function of y given x is strictly 0. So that's going to basically be the integral between 0 and 1 upon 2 of this function here. And this function is only non-zero in this region. So this is the conditional PDF that we evaluated on the previous slide. Okay, and we integrate with respect to now with respect to y. Okay, so we can take the factor 3 over 17 outside the integral, and now I'm integrating 4 with respect to y, it's 4y. The integral of 5y squared is 5 times y to the 3 over 3 is 5 over 3 times y to the power 3, and I'm going between 0 and 1 upon 2. This function when y is 0 is 0, so I don't care, so I just evaluate this function when y is equal to a half. And if I do that and multiply by 3 over 17, apparently the answer is 0.3897. Okay, so that's the conditional probability that y is less than or equal to a half given that x is equal to 4.5. Okay, part C is done. Now part D. Given that the drive-in facility is busy 80% of the time, what is the expected proportion of time that the walk-in facility is busy? That is, I want to compute the conditional expectation of y given x is equal 4 over 5. Now this sounds really horrible, but the only difference between what we did here and what we did here is the integration range is 0, 1, and I need to multiply the conditional PDF here by y. Okay, remember that the definition of the expectation of a random variable is equal to the random variable itself, y, multiplied by its PDF. And in this case, the PDF is a conditional one. Okay, that's the only complication here. Apparently he hasn't decided not to tell you how to do these things, but we're going to do it by example. So the expected value of y given x is equal to 4.5 is the integral over all possible values of y times the conditional PDF of y given x when x is equal to 4.5. We integrate over all possible values of y. Very good. Okay, now this conditional PDF of y given x is this thing, I hope, and this is the factor of y, and the region is 0 to 1 because again, otherwise the density function is 0. Okay, and now what we're doing is computing this integral with respect to y over the interval 0 to 1. Remember that in this case we are going to get a number, it's an expectation, expectations are constants. Okay, so we take the factor 6 over 34 outside, the integral of 4y is y squared times 2. The integral of 5y to the power of 3 is 5 times y to the 4 over 4 is 5 times y to the 4 over 4. I just said the same thing twice. Okay, and this thing is integrated to the region 0 to 1. Okay, so again, with y is 0, I don't care. If y is equal to 1, I get 2 plus 5 over 4 times 6 over 34 is apparently 0.5735. Okay, right, let's see example 5. Let's do example 5. In fact, example 5 is very much more complicated. And we've got some time, so let's try and work our way through it. Well, complicated, it's not that complicated. Okay, so, let x and y be uniformly distributed over the triangle with boundaries x is at most y in greater than or equal to 0, and y is in the interval 0 to 2. Okay, and what this means we're going to work out in a moment. Let's first of all think about what is the joint PDF of x and y. Okay. So let's think about this. It's going to take us some time. So what does it mean for x and y to be uniform? What that means is the joint density function of x and y on the defined region is that it is precisely constant. That is to say that the joint PDF of x and y is a constant k, which I don't know what it is yet, over this region. Okay. Now, what is the shaded region? Well, the shaded region is basically this triangle. So in this triangle, y is between 0 and 2, and x must be at least 0. Y must be at least x. Okay. So this is the triangle. So basically our PDF is k on this shaded region and 0 otherwise. Now the area of this triangle is basically 1 upon 2 times 2 times 2 is basically half the size of half the area of the square, if you like. Okay, so that means that basically the PDF must be equal to 1 upon 2, I guess. Okay, so okay, you can do it if you like. Yeah, okay, you can do the integral or you can guess like I did. Okay, so if you would prefer, so in order to compute the integral, so the density function is k, but remember now, in this interval here, now I'm going to integrate with respect to x first. So x goes between 0 and it hits the interval y. Okay, and y goes between 0 and 2. So my integration domain is 0 and y and 0 and 2, as I just explained to you. You can integrate with respect to y first and then x, and if you do that, y goes between x and 2, and x goes between 0 and 2. Okay, you can do it a different way. But we're doing it this way. Okay, so now what do I have to do? To integrate the function, I haven't got any problems, right? Because I take, well, okay, you want to do this. So integrate with respect to x, I get k times x, and x goes between 0 and y. So x is 0, doesn't matter, so I get k times y. And now k times y goes between 0 and 2, so k times y squared over 2 between 0 and 2. Okay, that's 2 times k. Okay, that's what I said, is basically that k is going to have to be, so this thing has to be equal 1, so k must equal a half. Otherwise you cannot get that. Okay, you could have done this a different way. So as I said, I guess the answer, and how did I do that? Because I know the interval is 2, so I must have the integral, the area times 2k must be equal 1, so I get k as a half. That's another way of doing it. Okay, because I know I don't have to do any integration to work out that the integral of that triangle is precisely 2. Very good. So the joint PDF in this case is equal to 1 upon 2 if x is in less than or equal to y greater than or equal to 0, and y is less than or equal to 2 and bigger than 0, and it's 0 otherwise. Okay, that's a uniform distribution over a triangle. Very good. Okay, so that's part A. Now what I want to do is I want to find the marginal PDF of x and the marginal PDF of y. Now these are more complicated than any of the examples we've seen before because the ranges of x and y are intrinsically linked. Okay, so I have to think carefully about computing these marginals. I cannot just do them very easily, and we will see why in a moment. Oops, sorry. Okay, part B. Oh goodness me, part B. Okay, so now the marginal PDF is just written it down. I haven't done anything there. Okay, marginal PDF of x. Okay, so now I know what? That basically I have to integrate the joint PDF of x and y over all possible values of x, of all possible values of y. Okay, so this is the joint property density function, is 1 upon 2. Now the key point is, what is the region of y I need to integrate over? Well, now this is the key point. I have to integrate over y, so y goes between x and 2. Okay, so that is why he has x and 2 here. And of course, at the same time, the random variable x is constrained to the interval 0 to 2. Otherwise, I get back 0. Okay, so this is the joint PDF, the integration limits as I've explained. You integrate with respect to y and I get 0. So this integral now with respect to y is y over 2 between x and 2 when x is in this interval. So now when y is equal to 2, I get 2 over 2 minus the case of x over 2, so I get 1 over 2, 2 minus x, if x is in this interval, and I get 0 otherwise. Okay, so you have to be careful because, as I said, the range of integration for x and y are correlated, if you like, not correlated in a statistical sense, but they're dependent. Now the marginal PDF of y, how do I get that? Well, it's the same game. Okay, now I take my region and I'm integrating with respect to x. The region, yes. So x goes between 0 and y. Okay, I hope I get that right, otherwise I've got something wrong. Yes, the integration region is 0 and y, and now the PDF, joint PDF is 1 upon 2. I'm integrating with respect to x, and remember y is fixed in the interval 0 to 2. Okay, and again, so this again is very similar to what we did before. So I integrate this thing between y and 2, so that's x over 2 between 0 and y is y over 2 if y is between 0 and 2. And of course, as I've said, because if y is between 0 and 2, is not between 0 and 2, that the joint PDF is naught, hence the marginal is naught. Okay, that's part B. So now we go to part C. So now we want to find the conditional of y given x and x given y, okay, and then we want to find, that's pretty straightforward because we've got the marginals and we've got the joints, so we're not really doing anything more complicated in part C, I think. So part C, so the conditional PDF of y given x, again, remember x is constrained to the set 0, 2, is just the joint divided by the marginal, and the joint is 1 upon 2, and the marginal is 2 minus x over 2. X, don't forget here, this is important, right? Y is at most 2, but it has to be at least x. So we've conditioned on fixing an x, and an x we condition on must be between 0 and 2. Now for the conditioned x on, the conditioned x, y must be at least as big as x and bigger than 2. Okay, it's important. You cannot, you must take into account the fact that y was bigger than x from the beginning. Okay, so then this thing here is 1 over 2 minus x, in this case, for x in this region. If, for example, x is 2.5, this is going to be 0. Okay, you cannot condition, well, it's not defined actually, because you can't divide by 0. Similarly, for the conditional, oh, what is he doing? He's just, okay. So this is just a function we wrote down. So basically, if x is equal to 1.5, well, I have 1 over 2 minus 1.5 is 1 over 1.5 is 2. And y must be bigger than 1.5 and less than 2, and 0 otherwise, as an example. Okay, now the conditional on y, x given y, so remember that x, again, y must be between 0 and 2, okay, otherwise I divide by 0. So that's the joint of x and y over the marginal for y. The marginal for y was y over 2. The marginal joint was 1 upon 2. And remember again that x is at most 0, but it must be less than or equal to y. It's very critical, again, you get that straight from the definition of the ranges. It's very important, otherwise you're going to get some funny behavior, okay? So this thing at the end is 1 over y in this range, okay? So as he says, basically if y is 0.5, the joint conditional PDF of x given y is f of x given y is 2, if x is in this region and 0 otherwise, okay? So again, this has been defined. You know y, so that's fine. So if y is a half, then it's going to give you the upper bound for x. All right, okay, so let's do part D and then we will finish. So we might finish like 1 or 2 minutes early. We want to compute the probability that x is less than or equal to a half given that y is equal to 1. Okay, this is not very difficult in some sense because we have done all the hard work already. Okay, so we know that the conditional PDF of x given y, if y is equal to 1 is equal to 1, okay, that's from here, y is equal to 1, and x goes between 0 and 1. Okay, this is a uniform distribution, and now I want to compute the probability that x is less than or equal to half for this density function. Okay, so I can tell you it's a half without doing anything, but if you like, let's do it. So this is the integral between the lower limit, 0, and a half of the function 1 dx. That's just basically equal to 1 over 2. Okay, and there we have to look at part E. Part E is almost done, almost ready, very easy to do part E. Now I want to find the joint probability that x is less than or equal to 1 and y is less than equal to 1. Okay, so this is the integral over this region of the joint PDF. Okay, so hopefully he's written down the region for us. So the probability that x is less than or equal to 1 and y is less than or equal to 1. So now remember that our entire integration region is this triangle. But now what we have is that x must be between 0 and 1, and y must be 0 than 1, and y is bigger than x. So our integration region is this triangle. Okay? Again, when you do this type of question, you should just draw down the xy plane and work out what's the region you're integrating over. He wants to integrate with respect to x first, so x goes between 0 and y goes between 0 and 1. Okay, so this is where these integration regions come from, 0 to y, 0 to 1. Okay, and the joint PDF is 1 upon 2. Okay, so now all I have to do is to compute the integral. Well, I integrate this with respect to x, and I get x over 2, but x over 2 between 0 and y is y over 2. And now I integrate y over 2 between 0 and 1. The integral of y over 2, my good, is y squared over 4 between 0 and 1, which is 1 over 4. If you like, right, you didn't have to do any of this work because this is a uniform distribution over this triangle, so you could work out the area of the triangle, which is 1 upon 2 times 1 times a half. It's a quarter, right? You could have done that. It wouldn't be equally acceptable, but this is the formal way to work it out. It'll only work, that, by the way, the answer I just quoted only works in the uniform case. It won't work otherwise, obviously. I'm going to get something else. Okay, and I think that's it. I think there's no point to start section 3.4. So that's it for today, and I'll see you on next week, Thursday at LT26. Thanks for your attention.